All right, I think we're going to get started here. Welcome everybody to AGU. Thank you for coming to our session on the applications of space weather research. Just want to very quickly mention, we'll continue the discussions in this session tomorrow in the early and late morning sessions. And also, if you can, please stop by our poster sessions both tomorrow afternoon and again Wednesday morning. Now I'm going to kick it over to James, and you can invite the speakers up here. Thank you.
All right, so our first invited speaker is Chief Scientist of NOAA-Space, Howard Singer. Will be talking about the research to operations to research cycle at NOAA Space Weather Prediction Center.
Thank you, James. Thank you. And how do I control things? Or you just hit this. Good morning. Thank you for the invitation to speak here. At the NOAA Space Weather Prediction Center, we provide forecasts, watches, warnings, and alerts for the civilian sector. And there's a continual need because of that in order to improve the predictions and forecasts that we make. So because of that need, we conduct research to operations and take advantage of research to operations and operations to research. And so that's what I'm going to be speaking about this morning. There's a lot of motivation for this. I'm going to talk a little bit about the National Space Weather Action Plan, and then I'm going to talk a little bit about one view of how this whole process can work to really benefit our nation. And I'll talk about some of the models we have at Space Weather Prediction Center, as well as some of the challenges we have. So first of all, I got to find out where I turn. Okay, I need this keyboard. Sorry. Let's see if that works. Okay. So there's a renewed interest in space weather transition and operations because of the National Space Weather, a lot of activities in the National Space Weather Policy. Many of you have heard about the National Space Weather Strategy and Action Plan, which was issued just about 2 years ago. And following that, there has been a executive order, which was issued a year later. And then there's also a Space Weather Research and Forecasting Act, which was passed unanimously by the Senate and is now working its way through the House. In addition, there's a new website that you can go to learn more about the Space Weather Operations and Mitigation Plan, and that's at swarm.gov website, and so that's quite a useful website to see. And there's a couple things in that Space Weather Action Plan that are particularly address the research to operations and operations to research activities. One of those gives the lead to NASA and NSF, but in collaboration with DOC and DoD, to develop a formal process to enhance coordination between research modeling centers and the forecasting centers. The other, on the flip side, is that DOC and DoD, in collaboration with NASA and NSF, are charged with developing a plan that will lead to the improvement and testing and maintenance of operational forecasting models. There have been a number of recent activities related to this. One is that we held a community workshop about a year ago in Boulder to get input from the community about how we conduct research to operations and operations to research. And that plan was commented on by many of you here probably in this room. And so that's going forward, and eventually that will be made public. In addition, there's already some really great things happening. One is there's initiated a NASA, NOAA, NSF Operations to Research pilot project, which it's a funding opportunity, and you're going to hear more about that, I expect, in the near future. So there's other motivations besides national policy, and motivation for doing this work comes from our customers. This is just one illustration of how we get indication of the customer need. This shows over more than a solar cycle is indicated by the black line. It shows the growth in a customer subscription service that we have that was started in about 2005. And it's really interesting to note that you can't quite see it here in the blip at the end here, but during the month of September 2017, just past September, we saw 12 times the average monthly growth of customers, and that was likely due to the response to a geomagnetic storm and the activity that occurred during that early part of that month of September. In addition, even though it is a small solar cycle and that we've had relatively low activity, we still see customers that are affected by things like solar flares, solar particle events, geomagnetic storms, all during this 3-day period that you see here where the KP index got up into large storm levels. And so we were hearing from customers who run GNSS, emergency management customers. There were things like the Miami airport losing HF comm while they were routing traffic due to the hurricane. Looking at Dan Baker here, I think you once wrote an article in EOS about the confluence of having hurricanes and having space weather storms all at the same time, and the impact of that on the nation. And so there's still a lot of impact. So we have a lot of motivation for conducting research to operations and operations to research. And this just shows a few examples of some of the ideas that have been put forth in the past about taking research and bringing it into the operational environment through going through a test bed and transitioning that into operations. This is a fairly linear picture of how one proceeds from research to operations. There have been other pictures drawn up, such as during the National Space Weather Program many years ago, which had a similar picture of taking research and research and modeling and observations and so on, and putting that into the space weather forecast arena, where then it could go to serve customers. There is some feedback indicated here, and there are other pictures that have also been drawn at other times of how one conducts research and gets that into operations. But with the National Space Weather Program, with the National Space Weather Plan, Action Plan, there's been a renewed emphasis, and I think some of this came out of our meeting we had about a year ago, which really emphasizes this cycle and feedback. So it's not just a linear system, but it's where you go from you could break into the process anywhere here on this scheme, and you could go from operational and customer needs to going to the basic and applied research community for tools that are useful. Those have to be validated, and then they can be transitioned onto NOAA or DoD supercomputers, and then support the operational community. Well, I know you're all thinking here, you got your arrows going one way, and they shouldn't all just go one way, and so they don't. They go every which way. There's a lot of feedback in this, and there's a lot of communication between each one of these types of activities, and that's really important to conducting an effective research to operations and operations to research capability. So many people understand research to operations. I think we all know for many years that you take, research develops models, they develop observations, and then those are put into the to the operational community where they can make a difference, where they are useful. But the operations to research part of it, I've been asked many questions about, well, what does that really entail? So I want to show you two figures, this one and the next one. Both of them have research to operations and operations to research elements, but they're just going to go in different directions to show some of these connections. So first of all, if we start out with operations to research, and that's going from here to here, what are some of the sorts of things that have to take place? You have to communicate operational priorities and requirements to the research community. You want to make those operational models and data available. Things we're running here in operations, you want to make those available to the scientific community, both to use and to test and to maybe upgrade. And when you go from this research group to the test bed where you want to evaluate those models, you have to make available models and data that are really ready to fill some operational need. And then going from the test bed to this transition, the models and data are evaluated, they need to be tested, validated, and prepared for use in an operational environment. And then going to operations, the models and data here need to be run on operational computers, made autonomous, made robust, and so on. But that's not the whole picture. because it goes the opposite direction as well. And here, when we go from research to operations, what sort of activities need to take place? Well, the research community wants to inform operations about models and data that are perceived to be relevant and ready to use. They may train operators on how to use those models. You may even have models that don't go around this whole process, but some, which I'll show you later in one example, which may just go into into an experimental mode of use. In going also from operations to transition, here you've got people who are working on transitioning the model into operations, but they're going to get a lot of feedback from the actual operators and forecasters. They need to get feedback on, well, what sort of displays and products do we really need that's going to be useful? How do you tune what your output is to make it valuable to the forecaster? You've got a lot of things you can do, and so somebody's got to establish some priorities for you. So these are some of the product priorities that can come from the operational community into those who are doing the transition. The transition folks have to tell the people doing the tests what sort of metrics do you want for evaluating products, and recommend validation and performance studies that can be done to make those tools and products more useful. And finally, going in this direction from the test bed to the model developers, the scientists, is requests for model documentation. What settings do we use to evaluate the model? So these are the sorts of activities and one way of viewing that whole process. So I've just, I think we went too far here. Going backward. There we go. So this is just one example of that process that I've just been talking about. It's an example of using the geospace model transition where we brought a geospace model into operations about a year ago, and that's used for predicting the magnetic variations that are seen on the ground and that are impacting space weather customers such as the power grids. So it started with a need from the power grids, from the customer. And that need when we go out to the research community, the basic research community, and say, okay, what models do you have that are available? And there were a number of MHD models and empirical models that could maybe satisfy that need. Then they went into a testbed arena where they went into the CCMC, where they were actually evaluated for how capable those models were. When we saw that there was positive skill, they went over here to the NOAA supercomputers, where they could be run and on those supercomputers to produce products, which would then come back to the operations center, but now they're supporting the operations center that I've changed here. And then the operators find out, well, this doesn't do all I want, maybe I want it to do a little bit more, so instead of a basic research, I've changed that to applied research, and you just continue going around the cycle. But there's more room here. There's a big gap in the center. And so one of the things called out in the National Space Weather Action Plan is an R2O2R center or capability that can be formed in the future that can help to do things like mirroring the operations that are going on here and making things available to the science community, improving the operational models, data, and products. By the way, I often maybe have been saying models, but I mean data and models, observations and models that need to be transitioned for use. There's validation and testing. There's helping to work that interface between the various activities that I've shown here. So this is also something that has been spelled out in the R2O to R document that people had an opportunity to comment on. So now I just want to mention a couple things about some of the models running at SWPC, at Space Weather Prediction Center. We've had the numerical model, was the first one, large-scale numerical model that came in, was the Wang-Shili-Argy-Enlow model for predicting the background solar wind and for predicting CMEs and what their time of arrival is. We've recently put this geospace model into operations. You may have heard Michelle Cash talk about that in one of the earlier sessions today, about the validation that's going on for how well this model can provide the magnetic variations that are seen at the surface of the Earth. There's work going on right now. It's a one-way coupled whole atmosphere, ionosphere, plasmasphere electrodynamics model. Couldn't fit that all in on the screen there. And that model will be useful for predicting conditions in the ionospheric environment. And then there's an E-field model, which is really what the power grid folks want, which is to take those DBDTs, convert them to electric fields using things like ground conductivity, and then coming up with the geomagnetically induced currents that flow in the power grids. I just wanted to quickly mention that we're working with RBSP, Van Allen probe folks, and this is just, we've had for a long time a geosynchronous orbit. We've had GOES satellites telling us what the radiation belt environment is, but now with the Van Allen probes, the folks working with the folks at Johns Hopkins and others, we can put together a picture of what's happening inside of the Van Allen radiation belts, put a test product into operations, which was just going straight from the research to operations, just straight from the research bubble to the operations folks as a test product. So space weather forecasting is going to advance through new and sustained observations, through models, but what I've been really focusing on here is that we need advances in space science understanding, like when is a flare going to occur, a solar energetic particle event, a coronal mass ejection. These are just some of the types of things that are needed to better our predictive capabilities and the transition and improvement of tools, data, and models through effective R2O and O2R. And these actions will, along with our understanding of the user needs, will enable us to serve customers with consistent, accurate, and actionable information. Thank you.
So I think we have time for maybe one question. Dan shot your hand.
Thank you for keeping a close contact between programmatic and scientific needs. Did you say the Science and Technology Council will continue to oversee these related activities to what we're talking about?
So that's what I understand as of now, but as we all know, the things are in a state of flux. We're not quite sure where. I think, we know Steve Clark is now at Office of Science and Technology Policy, and we hope that things will continue to flow through the system. I think we all view space weather as important and critical for the nation.
Okay. Thank you very much. So next, our invited speaker was Joe Minow, but unfortunately he couldn't make it. So Linda Parker will be briefing on his behalf. The NASA Space Environment's Technical Discipline Team, Space Weather Activities.
Right. Okay. Hi, thank you all. First of all, Joe sends his regrets for not being able to make it. He had a family situation come up that needed attention. So I will do my best to present his material. Looking for the pointer. There we go. So this talk is on some of the space environments, space weather activities that we're doing in the technical discipline team for NASA Space Environments. And specifically what I'm going to talk about today are the 4 activities that we've got going on right now with the JWST Space Environment Launch Constraint, the CubeSat radiation environments, and ISS radiation dose data, also the ACE real-time solar wind data stream, and a new database that we're trying to get put together with electrical properties for materials. So the JWST Space Launch Constraint is an assessment where we are analyzing the space weather constraints to help JWST avoid solar energetic particle radiation right after launch. Specifically, we're looking at 3 things. We're conducting an independent assessment of a proposed solar proton launch constraint. We're developing a launch constraint to avoid any extreme surface charging in the outer radiation belts, and we are evaluating the risk for internal charging during a radiation belt transit, and if it looked like there could be some charging issues, we'll develop a launch constraint if required. I do want to emphasize that JWST is designed to operate in the space environment. The goal of this specific activity was for the time right after launch to ensure that the exposure to any possible extreme environments during that critical time of operation is not a problem for JWST. So otherwise, JWST is fine. On the right, I have just two images of some of the software that we use to look at the launch constraints. These particular images are greater than 50 MeV flux, looking at solar proton events. And we simulate, so to speak, in the software a launch, and then look for 6 hours before the launch to see what the environment at that time would have been, as well as looking at after to see what the exceedances would be for the proposed launch constraints. The CubeSat radiation environment is an assessment that Mike Zapsos is looking at. He's at Goddard. And it's to characterize the radiation dose within the CubeSat structures using a 3D transport code like Novice as opposed to a 1D such as shield dose. And the results from this will then be given to CubeSat developers to help them design for their launches. So on the right, we see the cumulative probability versus array trace path link for 3 different assessments. One of them is an empty CubeSat, and then a 5-board CubeSat, and then in red is actually the CIDP box that's within the MMS spacecraft. And so the idea is to process the ISS microdosimeter data and compare it with the model results to validate the 3D modeling. And like I mentioned, this will be developed into a data product that after it's been formally approved by the NESC will be given to the engineering and scientific community. Also, he's doing a comparison of 1-year mission at 90% confidence level for 2 different environments. CubeSat that would be flown in a space station environment, as well as a CubeSat in the geosynchronous environment. Using, I'm going to point out what these lines are. The top black line is a solid sphere that was modeled with shield dose. And then the rest are modeled with Novice, and it's in order of descent. An empty box, 1 PCB CubeSat, 3 PCB CubeSat, and a 5 PCB CubeSat. And the colors are the same on the other plot. And so in decreasing on the, sorry, I just got you with the laser pointer. Decreasing on the chart is increasing shield dose. And so it shows that the 3D dose, back away, the 3D dose analysis and lower radiation dose at locations within the spacecraft are the solid sphere 1D results are more conservative than using the 3D results. So also, there's a miniature array of radiation sensors that's called MARS. And the goal of these sensors is to provide an array of sensors to monitor the radiation total dose on host spacecraft. And it was launched, it actually was developed by Aerospace and then transitioned to Teledyne for development. And it was launched in 2013 on the GLADIS instrument and flown in space station orbit. And over here is just one of the nodes for the Mars configuration, and then there's a 4-node array. And then here's the GLADIS experiment showing where the different Mars nodes are. And so the approach is to use this hybrid microcircuit to measure accumulated total ionizing dose for the whole mission. And let's see, the nodes are connected to a central data collector so that each node will collect the total dose where it is, and then the information is given to a platform for data handling. So some results from this, this is channel 0, showing daily dose rates for this particular channel is, you can see that the South Atlantic anomaly is really what shows up for this one. And I'll show in a second where channel 0 is. But as a comparison, channel 8, which has reduced shielding, so it's not as shielded as channel 0, not only has a lot of dose in the South Atlantic anomaly, and that actually extends out further than what the zero channel was, but it also has a lot of daily dose in the higher magnetic latitudes. This is an image of the mission average dose, and so node 0 is the same thing as channel 0, and it's in the GLADIS experiment internal on the nadir side. And then node 5 has 50 mil aluminum shielding, and it's on the zenith side. And so these daily images, mission dose images will also be developed. And the idea is to have all of this Mars dosimeter data made available to the science community through the Goddard Space Physics Data Facility, and hopefully that will happen in the coming year. So now I want to talk about the maintaining access to the ACE real-time solar wind data. Since Discover was transitioned into the real-time satellite for L1 solar wind monitoring, NASA and NOAA-SWPC have been working together to ensure that the ACE real-time data also is still able to come down and be available for people and companies that need it. The prime driver is NASA's continued need for the EPAM energetic particle data, and the Chandra X-ray Observatory program uses the P2 channel, which is 115 to almost 200 keV proton channel, for radiation mitigation. Also, the European Union Hesperia release tool uses the ACE real-time as well. Right now, we have approximately 60 to 70% daily coverage for the real-time downlink stream. And I just wanted to also mention that if anybody else there uses or needs to use the ACE real-time data, we would love to know about it, because we're trying to compile people that use it so that we can ensure that it does continue to happen. Right now, this is a look at the ground station tracking that is downlinking for the ACE data. And there's two in Germany, the DLR, which is the German Aerospace Center, as well as the University of Kiel. And we use the NASA Deep Space Network and the NOAA Wallops Command and Data Acquisition Station. And so all of that gives us roughly 60 to 70% daily coverage. We're still working to get to fill the gaps, the data gaps in the Asian sector. And we've got a couple of leads on hopefully some facilities that can help us, but nothing is set yet. But we are working to have that filled. And then finally, the technical discipline team is developing a materials electrical properties database to help support charging analysis for space weather events and space environments analysis. The idea is that this database would house things that are needed for surface and internal charging analysis, such as atomic number, density, the volume and surface resistivity, dielectric constants, secondary backscatter yields. All the things that you really need to understand the material properties and how the particles penetrate. We do plan to make this database available to the community. It will be through the MAPTIS website, which is NASA Materials and Processes Information System. This is their website, but I don't think that's going to be the database website. It'll be something that has hopefully charging database or something in it. But when we get that outward facing, we'll email the community so that you know about that. And if anyone has any test information that they would like to put into the database, I would be more than happy to get that. Because one of the things that we want to do is not only have these material properties, but we want to have links to where it came from or how the testing was done. Was it done in vacuum? Was it done in ambient? And if there's a test report that's associated with it, we'll have that PDF available for it as well. And just to show the importance of these materials, on the right is a novice run for a geostationary transfer orbit of just a general spacecraft, using the AE8 Solar Max at 0 degrees inclination. And we have here a conductivity of 10 to the minus 15. And so you can see that as the spacecraft goes through the environment, in and out of the geostationary transfer orbit. For this case, the charging decay time was 147 minutes. So as it's going through and building up charge within the material due to the conductivity of the material, it will then start to decay as it leaves the environment. However, if you decrease the conductivity, which increases the resistivity, then the decay time for the material increases. And if the resistivity is too large, at some point you're not going to be decaying inside the material, and you're just going to continue to build up charge. So that's why surface and internal charging needs really good material property information, and we want to make that available as best we can to the community for their use as well. And that's all we have. So, are there any questions?
Really got a scan in this room. Yes, Rick.
Do you have a time frame for when you think that materials database will be published?
So I'm working on it right now with the Maptis people to get that splash page and to figure out how the properties need to be put into the database so it's best accessible. It could be outward facing as soon as a few months from now, but there's not a whole lot of information at the moment to put in there. So, we're hoping sometime in early next year that it would be outward facing.
Other questions? All right.
Okay, thank you.
Thank you very much. Our next speaker is Matthew Carver, who will be speaking on cross-calibration of GPS proton data with GOES EPS, a new data set for space weather research.
Okay, thanks very much. So, like you said, my name is Matt Carver from Los Alamos National Lab, and I'll talk to you today about the GPS proton data and the calibration we just performed. So, a little bit of background. The GPS constellation nominally consists of 24 satellites, and you can see it pictured here. We're on 6 different orbital planes at an inclination of 55 degrees. And so you get continuous coverage at a wide range of longitude as well as latitude with a 4-minute data cadence. And basically, any point on Earth can be seen by at least 4 satellites at any one time. And so earlier this year, the energetic particle data, so electrons and protons, that's collected by the GPS satellites was released and made open to the public. So this corresponds to more than 187 years of satellite data since 2001, and roughly 2.5 satellite years of data is added every week. And so this is exciting because it's the largest space-based electron and proton data set available. And you can see on the bottom here a map of temporal coverage of our GPS satellites as a function of dates. And you can see in the back the sunspot number showing we have data for a full solar cycle. And we also have GOES and the Van Allen probes up top for comparisons. So the instrument that is making these measurements is called the Combined X-ray Dosimeter, or CXD for short, and it's sensitive to both photons, electrons, and protons. And it's currently aboard 21 GPS satellites, and you can see a rough diagram here. And so it measures protons and energy ranging from 6 MeV on the low scale with the highest channel greater than 75 MeV. It was designed to be used in verification of the Limited Test Ban Treaty, signed in 1963, so making sure that nobody is detonating nuclear weapons above ground. But it's not immediately obvious that it can perform as a science mission and be comparable with all the other ones that are available, so we need to do a cross-calibration to show that. So this was done already in 2016 for the electron data with the Van Allen probes, and so we've now chosen to do that with the GOES mission or GOES EPS instrument for the protons. not only because it has overlapping energy ranges with ours, but because it also recently underwent its own cross-calibration with a NASA IMP mission. So the procedure we followed was to use solar energetic particle events because they offer a very wide range of both energy and fluxes to use for calibration. But to do this, we've got to make a couple assumptions. And so the first is that these energetic particle events are relatively isotropic across the scale of the Earth, so that even though we're in two different orbits and altitudes, we're going to see roughly the same flux. And that's also taking into account that if we're at large enough L shell, the energetic particles are going to be minimally shielded by the Earth's magnetic field. And so if we take these assumptions, we can then define what we call a temporal coincidence when our GPS satellites are in an L shell greater than 10, and the measurements from the EPS and CXD are within 2.5 minutes of each other. And so with this defined, we've got something like 30,000 conjunctions that we looked at for this study. And once we have these, what we end up taking is the GOES EPS flux measurements that we consider valid and cross-calibrated, convolve those with our detector response to get an estimated number of simulated counts on our own instrument. And so we can take that and plot it on the y-axis versus what we actually measure on the x. And you can see that we have a good linear correlation, but we're not on the y equals x line, which is what would be ideal. And so what we end up doing is applying an overall response factor to then bring it into agreement here. And so this is just an illustrative case, but for our 5 proton channels, you can see here for all of our conjunctions that we show good agreements, and we list our linear fit parameters on the slots. So these response factors are going to be satellite as well as channel specific, and they range from a roughly % level to a factor of 2 in a worst case, and I have all those numbers in the back if anybody's actually interested. So we have these now, let's say, calibrated channels. What we want to do next is calculate proton fluxes, and so what we do is take all of our 5 proton channels at once, do a simultaneous fit to a predefined spectrum that has contributions from both the galactic cosmic ray background as well as our solar energetic particle contributions. And you get a differential flux, which I've pictured here on the bottom for a day in 2006 and 2014 on the right. The black points are what we calculate, and then red overlaid are the EPS measurements. And although the Van Allen probes are not used in the calibration, we do plot them here when available as green. And so you can see that we do have good agreements. Down here where EPS is below ours, this has already been background subtracted for EPS, but ours clearly has this galactic cosmic wave background in there, so you'd expect some deviation. So this is the differential, but you can also take a look at the integral fluxes versus a function of time to get a time series for different intervals. So this is from this interval on the left from 2006 in December, and again on 2014. And what we show here is the greater than 10, 30, and 60 MeV fluxes. EPS is in blue, red, and green, and then the CXT measurements are black on top of that. And this is on a 20-minute average from all of the available satellites in the constellation at that time, so it ranges from between 6 or 7 into 12 different measurements that go into this average. And so qualitatively, you can see that we have very good agreements across these orders of magnitude in both flux and energy, but it'd be nice to take a little more qualitative look at this. And so we can take this and plot these integral fluxes. So again, the greater than 10, 30, and 60 MeV fluxes plotted on a 2D histogram. This is what EPS measures, and this is what CXT measures. And you can see that in general we have good agreement across this region. You can see that we have some spread here in the greater than 10 MeV fluxes, but we'll take a closer look at that here in a second. But we list down here in the bottom our linear fit parameters, so the slope for various energy levels, as well as the interquartile ranges for this ratio of CXD fluxes to EPS fluxes. And so we can take a closer look at some of the disagreements we see in the greater than 10 MeV fluxes and reasons why we might see that. And so what we have here plotted again are the greater than 10 and 30 MeV fluxes for CXD and EPS on top, but below that we also have the raw channel counts from the first 3 proton channels of CXD, which go into this calculation for the greater than 10 MeV fluxes. And so there are areas highlighted where you can see features in the EPS flux that are not present in the CXC. So we have this shelf here that's not present here, but if you look in the raw counts, we don't see those, and so it's more or less impossible to recreate that without the raw channel counts. And another example is down here on the bottom. So EPS increases and has a secondary hump, which we fail to see where we have one increase and fall down with CXD. And so we are attributing these disagreements in the greater than 10 MeV fluxes due to the instrument sensitivity rather than the actual flux fitting procedure. And I think I've gone a little fast, but we have a summary here. And basically the idea is that the CXD is providing good quality proton flux measurements across this range of energies. In general, the data within the first and third quartile ranges of the ratio of CXD to EPS is within 20 to 40%. And so even though we have response down to 6 MeV for protons with a CXD, even the greater than 10 MeV integral proton flux is not well captured, as shown by the comparisons previously. And so we're going to recommend that users of this data set restrict their analyses to proton energies greater than 20 MeV without considerable thought as to why they would like to go down below and how it would affect their analysis. And so this data set is available now at this URL, but this updated flux calculation is not reflected in there. And so what we're planning to do is start that reprocessing shortly and hopefully have it uploaded within the next few months. But yeah, I think the exciting part about this is we've got this new great data set, so we're going to hopefully see a lot of new exciting data or analyses that just weren't previously available to do. So thank you very much.
Okay, time for questions. Yes.
At one slide, exactly how does the galactic flux perturb the correlation system? Say it caused a slight misfit with galactic flux.
Yeah, so I'll go back to this one. It's on the differential flux. I was trying to point out that you see that the EPS flux continues to fall, as you would expect from an SCP contribution. But this is already background subtracted, and so they've removed their background from it, where ours has this bump here at higher energies, which is directly due to the galactic cosmic ray. I don't know if that answered the question or not. Okay. Any others? Okay. Thank you.
All right. Thank you very much. Okay, so our next talk will be by Natalia Ganushkina, who will be talking about specification of electron radiation environment at GEO and MEO for surface charging estimates.
Okay, good morning. I'm going to present the results of our close collaboration with an organization called ONERA from Toulouse, France. And we did this work mainly during the projects funded by European Commission. And the motivation in a very general level is that we know that surface charging is one of the important satellite effects, and anomalies, to study the anomalies associated with surface charging is one of the main problems, and especially at the orbits where we have a lot of spacecraft like GEO and MEO. And at MEO orbit, we can have the worst situation since, first of all, worst in terms of the amount of the environment which can influence the surface charging. And the second is that we don't have much information at MEO orbit since we didn't have many flights there. So there are some effects due to surface charging. I'm not going to describe what they are, it's just very quickly that the electrostatic discharges causing electromagnetic interference to local degradation. We have also sustained arcs and system or mission destruction in the worst cases. ONERA very often gives this type of the examples, like individual examples of the permanent losses due to surface charging. They are one of the Japanese spacecraft, 8-month outage of the Galaxy 15, well-known spacecraft, of course, and large permanent power loss on 2 other satellites, 2 other spacecraft. So there are several, of course, guidelines to mitigate the surface charging effects, but at the same time, they were developed based on very limited data sets. And we have a current need to determine the risks of the extreme events present especially at GEO and MEO. And this part was provided by Dr. Matteo Velez from ONERA. And what they did, they analyzed the 15 of LANL data and at GEO from 1989 to 2005, and they used 6 different LANL spacecraft. They analyzed all the measurements from from those 3 instruments, and here they have they did a lot of statistical analysis, and this is one of the examples showing that there is a best correlation between the potentials for the electrons in the energy range from 10 to 50 keVs, and this range especially corresponds to the 8 and 9 keV thresholds from the previous studies of the surface charging environment at GEO, at LANL specifically. So they suggested that the fluxes in the energy range from 10 to 50 keV can serve as a threshold, as an indicator that the surface charging is going on at GEO. They developed actually, or determined, or whatever it's called, 4 different criteria for worst case environment based on LANL data. And they call them by different, these are 4 of them, they call them by different abbreviations. First is highest fluxes of electrons and at energies above 10 keV. Second, highest fluxes at all energies. Highest fluxes at low energies. And then these are based on the measurements of electron fluxes. And the 4th is the potential greater than 5 keV. So they selected from all of the 15 years of the data, they selected 400 events with worst case scenarios, worst case environments. And 2 guidelines that they used to make the comparisons is one of the European standard and another on the NASA standard. This is a very easy, very simple chart which we developed just to demonstrate when can we expect the surface charging event happening as dependent on geomagnetic activity. So usually what we think when we talk about extreme events, for example, intense storm, the larger the storm, the more the effect we get. This is not exactly true for surface charging because it's due to keV electrons. And here we plot all of the occurrences of those 400 events, and we separate them very simply using DST and AE indexes like storm phase, intense substorm, quiet time or unclear or isolated small substorm. And that's what we get, that it's not necessary to have even a storm to get a significant surface charging. So we can have a surface charging happening during isolated substorms, and from our work, isolated substorms, they can be like 200 or 300 nanotesla. So it's not a huge, like 1,000 nanotesla substorms in AE index. So what I was asked to do by ONERA, we have a fluxus at geostationary orbit. We want to know if we have the worst scenario at geostationary, what's going on, what will be happening at MEO orbit. Since we don't have the direct measurements, we cannot make like one-to-one comparison. Here it's happening at GEO, here it's happening at MEO. So they asked me to model the electron environment, since we have the inner magnetosphere particle transport and acceleration model for low energy electrons. So it's the model where we follow the electrons from the plasma sheet towards the inner regions of the magnetosphere. And then this model can utilize any of the background magnetic and electric field models. It includes the boundary conditions in the plasma sheet, which we developed very recently based on TEMIS data for the representation of the initial distribution in the plasma sheet. We take into account radial diffusion and the losses for electrons as electron lifetimes based also on the different modeling representations. So IMTAM includes many different types of the models, empirical and analytical model. And then it can output any of the distribution of the electrons with different energies. Mainly it's KV energies, which we are working with everywhere in the inner magnetosphere. And this model actually works online in real time, and the comparison is going on with GOES data. So this is one example, severe event for surface charging, April 5th, 2004. And you can see here is what was going on in the magnetosphere. So this is during the storm, but it's before the maximum of the storm. And storm is not so huge. And that's what we can see. This is the map of the IMPTAM modeling, the model of the electrons in the energy ranges from 1 to 300 keV. And this small cross shows us the location of LANO when the observation of this severe surface charging event happened. When we move our electrons to model our electrons, we find what I was asked to do. We find the location of the maximum flux at MEO orbit. If we have the beginning, when we are trying to find out this location, the beginning is in GEO, and then we move them forward and find the first occurrence where we have the maximum flux at MEO when it's reached that. Here is an equatorial plane, so it's 4.6 Earth radii, this location of the MEO orbit. How I determined the MEO there, I just put several GPS-like type of model of orbits, and then outputted the fluxes and try to find the maximum along them. So what we can see here is, this is the example, this is the explanation what we had. We had, I don't see very well from here, but you can see hopefully, yeah, no, there is no second screen. So IMPTAM was doing pretty well with LANO measurements to reproduce the LANO measurement and GEO, and that was our beginning, our somehow proof that we can do more or less okay, and then we move inward, we move to MEO. This is the output on the maximum location at MEO orbit, and you can see this, the factor which we have here is that in worst case at MEO we will have the increase of the KV electron fluxes by a factor of 2 to 10. This is the two standards, this European and NASA standards, and we also see that our flux, which we output in the worst case scenario, can be, again, orders magnitude higher than the worst guidelines given by those two standards. This is another example, just another thing, another surface charging event, but here we don't have any storm. We have a substorm, yes, going on, but we don't have any storm, and this is again the surface charging environment was on the different MLT. This is our maximum flux at MEO, and this is the same representation of the spectrum, LANO measured, IMPTAM modeled at GEO, and then at MEO and the standard. So we again see that we can have the environment at MEO orbit much higher than any standards give for this war scenario. So here we have 2 and 2.5 factor of increase in fluxes at MEO. And the last one, when I have very little time, but this is the event which very well modeled, of course, but not to model directly, but using the parameters to reproduce, to reconstructed the event which we call it that missed the Earth. So considered a very extreme event, and we did, and many other people did a lot of the analysis. What if this happens, and so on. So this is the reconstruction which we used based on stereo observations. We used published, of course, results on that event. And NLIL model was used to reconstruct the parameters of solar wind and IMF, which were not available by measurements. And Temerin and Lee model was used to reconstruct the DST. So the values are huge. So DST in maximum will be, in minimum will be 200 nanotesla. Solar wind dynamic pressure is also very big, 300 nanopascal, and velocity is 3,000 kilometers per second. What we have here is that what we're going to have at GEO and MEO. We don't have measurements since there is no reaction of the magnetosphere. Nothing came to the Earth. But we started to model this event, and we found the problem with that we do not have the model, and especially magnetic field model, to represent the variations of the magnetic field during this event. So therefore, this is a demonstration how all of our electrons just gone. This is the extreme event, but we don't have electrons, we don't have fluxes. And this is not because, well, I don't know exactly how to answer this question. Maybe it happens in the reality, we don't have measurements, but for this modeling approach, if we have, here we use Tsiganenko model, so, which was not constructed based on extreme events, of course, it's just the interpolation, possible interpolation. But the field lines become so stretched on the tail and so compressed on the day side that our electrons, they happen to be on the very high, on the larger L shells, and they are just lost from our area of modeling in the inner magnetosphere. So that's what we have. So therefore, we were able to estimate only in the beginning of the storm. And here we have, this is the same output that I showed before, and here we see the difference. These are the standards, and this is our own output. So you see the difference is more than one order of magnitude. So I see I don't have much time, so to summarize that, based on the analysis of Lionel particle data at GEO, 4 criteria for defining severe surface charging conditions were developed, and they were based on integral fluxes and also the spacecraft potential measured, and 400 specifically severe worst-case scenarios were determined, environments. So we modeled all the types of the worst-case surface charging environments with IMTAM, and what we get that IMTAM is output is comparable to Lionel fluxes at GEO, and therefore we can move forward, as I said, and try to model the environment at MEO orbit, which we don't know in reality what it is in details. So the electron flux at MEO can exceed electron flux at GEO, measured electron flux, by factors of 2 to 10 to like orders of magnitude easily can be reached. And the event which we try to estimate is that event which, extreme event, was the extreme event which missed the Earth. So all of the guidelines give the electron fluxes much lower than we can model, even in the beginning of the storm, since, as I said, the maximum of the storm we were not able to model reliably, since we don't have available models for the magnetic field, electric field, any model in which we can trace our electrons and see and calculate the fluxes at the MEO orbit. But this is it, the guidelines. And actually, I'm not talking about the recommendations, because ONERA has its own recommendation to how to mitigate these worst-case environments and how to provide the new guidelines for the worst-case scenarios. But this is our, not part of this talk, but that exists, their publications. Thank you very much.
So we have time for questions. Yes.
For the events that you could actually model, did you test the sensitivity to other magnetic field models or other electric field models to see how that flux level would vary?
Yes, we actually did that some time ago, and here I present the results which gave the best accurate, the best correspondence with the measurements. Yeah, so it's, this is Tsiganenko TS-05, which was developed for storms, but it's a long discussion how bad or good it is. But we try to find the best combinations, yes. Yeah, they vary a lot. Whatever you put as a background, whatever you put as a boundary conditions, you will get very different results, yes.
Just to follow up, have you talked to Sidnov or Grant Stevens about the TS-07 model? Because I'm not sure how far you can push it, but if there's fitting parameters that you could potentially set up to a particular storm.
Yes, yes, I know, of course, I know TS-07. I haven't worked with it a lot by historical reasons. just didn't, yeah. Especially for extreme events, because the Tsiganenko model, yes, it doesn't have any, interpolation is not what we see during the extreme events, maybe.
Yes, Terry.
Would you agree that for an extreme storm, like you said, you're not going to get a certain bunch of surcharge, right? And once you've emptied that plasma sheet out, what's going to give you a dense cold electron population?
If it's true in reality that these results are based on the modeling, and we don't have anything to prove that this modeling during the extreme event is good. So if it's true in reality that all of magnetic field lines and all the magnetosphere becomes so compressed on the day side, because it goes, do I have it here? There. So it is inside, geostationary orbit is outside. So magnetosphere is inside geostationary orbit, so it's so well close to the Earth. If it happens in the reality, yes, I don't think we will have a lot of surface charging during very extreme events. And this is actually what we see on the dependence of surface charging observations with geomagnetic conditions. We have a lot of surface charging going on during isolated substorms, but not intense storms. Yeah.
Independent of the size of the
Yes.
map, just the convection is going to bring all that through, and what's going to replace it?
Yeah.
So this is a shameless plug more than a question. So that scarcity of MEO data, next year the DSX mission will launch and go to MEO and have a comprehensive suite of particle and plasma measurements that'll hopefully provide a good validation set. Our next talk is Anthony Mannucci. We'll be talking about case studies of forecasting ionospheric total electron content.
Thank you very much. I'm very happy to be able to give this talk. Where's the pointer? Oh, here. Okay. I want to acknowledge my co-authors and also the model developers, and Aaron Ridley, Yue Deng, and Gabor Toth at the University of Michigan. We've used other models in this research. CCMC has been a great partner for us, and also the collaborative modeling. So, I'm going to go motivate the talk. Basically, we're talking about research to forecast conditions in the thermosphere, ionosphere with multi-day lead times. We're going to talk about, I'm going to talk about a high-speed stream storm that has an interesting case that sort of reveals the complexities of this topic. And I'm going to be making a proposal for how we move forward with CME-driven storms, which can be much more intense. Forecasting conditions in the thermosphere, ionosphere using global 3D physics-based models with 1 to 4 day lead time. That's our research focus, basically triggered by an earthward-directed CME or high-speed predicted arrival of a high-speed stream. You then try to make a 3-day forecast of how the ionosphere and thermosphere will be in a few days' time. It's analogous to a medium-range weather forecast, except it's strongly dependent on that external driver BZ, which has been difficult to predict, of course, but progress is being made. It's very encouraging, both on the modeling and the observation side. And probabilistic predictions of BZ are beginning to be made. The other problem is measurements of the drivers of the thermosphere, ionosphere are not really well sampled, and there's an inherent unpredictability of the thermosphere, ionosphere because of that, and because the ionosphere is so dependent on thermospheric conditions, and these conditions are difficult to measure and model and specify, it makes prediction much more difficult, but I'm suggesting pathways to progress. So our initial focus was total electron content. This is a derived quantity from one of these physics-based models. It's basically collapsing the three-dimensional model to a two-dimensional model. The physics is computed three-dimensionally, of course, but we can take the two-dimensional version of that and we look at it on a coarse lat-long grid to reduce the number of elements we have to predict. If you think about a weather model, you're predicting, or this kind of model in full 3D form, you're predicting essentially 10 to the 5th different quantities through the model. We're reducing it to 144 quantities TC over this coarse grid, and we have to do it every hour, let's say, for an hourly prediction. So it remains a complex problem, but it's a more manageable problem. And so the basis of these sorts of predictions are model outputs such as this. This is the total electron content from GITM, the Global Ionosphere Thermosphere model developed at Michigan. This is a snapshot of it. And this is a comparison data set. This is the global ionospheric map. It's a data product derived from measurements of global TEC. And even though it's not direct measurements, we understand the error characteristics of this product. And what makes it so valuable is it's directly comparable to a model output because it's a full grid. What I'm showing on the right is the difference between what the model suggests is going on at this epoch and the quiet time value of the model. And that's typically what you would want to do in a storm time prediction, is you want to know how is the storm changing the thermosphere conditions. That's a very important quantity that we've studied positive phases and negative phases of storms for many, many years. And you can see that this map is, of course, less in magnitude than that map because these coupled models only go to about 600 kilometers altitude. That's most of the ionization, but the measurement is the full ionization all the way up through the plasmasphere, but we can account for that. The real point is that when we did this study for June 2012, which was a very weak storm, you can see that the model predicted a very large increase in TEC in this region here, whereas the measurements suggested the difference between the storm time snapshot and the quiet time predicted not that much change. So why is it that the model is reacting so strongly to the storm time conditions? Our initial thought that there was something going on with the storm time drivers, such as the solar wind. The solar wind in these models is typically fed into a empirical model of high latitude convection. There are other factors that go in, so we thought that's what we would look at. This is another view of that. We looked at a certain one of these grids in 140 west and 15 south, and what this is plotting is the model, and this is the data product. So the black line is the model as a function of time. The black line is the quiet day repeated over and over. The red line is the model as a function of time going into the storm, and you can see in that region the model predicts very large increases in TEC, whereas the data product, which is based on measurement, has a quiet time value, which is similar in some respects to the model, but it doesn't show almost any response. It shows virtually no response to the storm. This is not what we expected for a weak storm like this. So this is a slice of the model and data products through this region here, where the increase is occurring, and so there's very, very many interesting information in this, and I'm going to talk about that. So the data product looks like this. So this is a slice in latitude through that longitudinal region, and you can see that the dotted lines are the quiet time, and the solid line is the storm time. You can see virtually no change, as I showed you before. The models, we ran both GITM and TIGCM, share many similarities actually in the quiet time, and you can see that they match very, very well in the southern hemisphere here, not so well in the northern hemisphere. They're off by a certain magnitude. Now, in typical forecasting applications, say in weather, people understand that if you run a model freely, you're not going to generally agree with observations. These models have very many solutions to them, and so they perform data assimilation to bring the model in line with the instantaneous conditions before they do the forecast. Well, we aren't doing data assimilation here, and I'll talk about that a little later. So there's certainly not that great agreement in the quiet time, but that isn't our focus. Our focus is how does that change during the storm time? And you can see that whereas the data product did not change very much during the storm time, the black solid line, the models changed drastically during the storm time, and what they particularly did is they expanded the reach of the equatorial anomaly. So the reason this very large change in TEC occurred in the models in this particular region is it's a region where there's a very sharp gradient as we move away from the equatorial anomaly region in general, and the model and data capture that gradient pretty well. But what happened is the model wanted to expand the anomaly, so you're expanding TEC right in a region where it's dropping rapidly during quiet time, and you're getting very, very large changes. So we thought somehow the drivers are doing this, or what is doing this, we didn't know. We thought first we'd look at the storm time conditions, because that's really what we typically, when you're talking about a storm, you think of the solar wind conditions as what changes most dramatically. This coming in of the high-speed solar wind, that's going to be the driver here. F10.7, we didn't think that was a big factor, but it turns out F10.7 was a big factor here, just coincidentally. So what we did is we ran separate test case for the model, and this is again the quiet time and different model runs. The first model run we did was with a quiet solar wind in the actual F10.7. This model run in green almost approaches the full real 10.7 and real solar wind. Now, in a forecast, you'd replace the real solar wind with a forecasted solar wind, but we're just investigating what the models do with the actual solar wind in a forecast type mode. And you can see that when we replaced the solar wind, the high-speed stream with the quiet solar wind, it almost reached what it did with the disturbed solar wind. Whereas when we replaced the quiet solar wind, the storm time solar wind With a quiet F10.7, it dropped quite a bit. So whereas the model was trying to increase TC in that region due to its own internal dynamics, it got a big acceleration when we put the actual F10.7 in there rather than the quiet F10.7, but the effect of the solar wind was actually pretty muted. There's a third test here I won't go into, but the point being that it also turned out that the F10.7 happened to be changing rapidly around the time that the storm hit. They're generally not going to be connected. The F10.7 reaches us instantaneously, but it turns out about when the storm was hitting, the F10.7 changed rapidly. Now that alone should not create a model error because we experimented with the actual F10.7 as well, and that alone, the fact that it was changing rapidly, shouldn't alone cause the error. So although in general, if you're trying to make a 3-day forecast and F10.7 is changing rapidly, that is a problem. But what seemed to occur is that the model TUC response to the June 2012 storm depend more on the F10.7 flux and the interplanetary condition. Whether we used a forecasted F10.7 flux, when we used the real one, it really showed a dramatic, or the real one, I guess I didn't say that right, but let me just say that, okay, but the real point we're trying to make here is that the F10.7, when we use the actual F10.7 to drive the model, the actual F10.7, not the forecasted one, the model overreacted to that F10.7. So what that means is the proxy driver for F10.7 started to get wrong. The EUV that we derive from the F10.7 proxy started to go way off. Whether that's correlated with the fact the F10.7 changed rapidly or not, we don't know. But that's something that you have to be careful of in a forecast. For some reason, the proxy started to go way off and created these large model errors, both in TIGCM and in GITM. Would data assimilation have been useful in this case? Probably so. We could have matched the model and the data that 3 days before the event reached Earth, and we probably would have gotten a somewhat better result, but trying to forecast 3 days out is tricky anyway, so we're not stressing data assimilation in this type of research, even though it's been very valuable in few-hour kind of forecasts. For 3-day forecasts, we haven't stressed it. But what the main point is that even for this weak storm, it's highly complex to forecast over a coarse grid. So in the limited time I have, I just want to make an analogy here to the fact that space weather forecasting is not new, okay? And in fact, people have been doing geomagnetic forecasting for many years, and we saw an example of it recently where people simulated the DST index using solar wind conditions. So our thought is, could we do something similar to reduce the complexity of the forecast? Could we create an index that we try to forecast, an index of the ionospheric behavior, rather than a full 2-dimensional or 3-dimensional map? This index would be derived from the model, similarly to the way the geospace model estimates KP, but not try to estimate a full 3-dimensional map, or even a 2-dimensional TC map. And the analogy here is the AE index, which is very interesting to consider because the AE index is used a lot in research. It's used a lot in forecasting applications, but it's a very strange index because what it basically is, here it is right here. It's the values of the magnetic field measured at 7 magnetometer stations. Then you take the largest excursion at each station and you form an index from it. So where that magnetometer value is coming from is constantly changing. It can come from one magnetometer station here, then another one a few minutes later, a couple hours later, and it's just formed into an index. So it loses all spatial information, but this has still been an extremely valuable index for people to use for scientific research. So why not something analogous, and I'm almost out of time, for CME-based storms, and I'm not giving you examples of these, but we have analyzed these CME-based storms. I'm showing you only the TEC map here, not the data product, not the model, and what I'm plotting is a very simple quantity. It's the global maximum TEC based on the map. Not only based on the map, based on the coarsified map. So it's a very coarse number, and we could do a better number probably going back to the actual data, which could be available in real time or in many ways. But you can see that this global maximum TC, now what I'm plotting here is a storm period. I'm not doing a common epoch analysis. Just somewhere in this 3-day or 4-day period, you will find the peak TEC. You will find the storm has been occurring, and you can see for the October storm and for the November storm, there's a very clear signature the storm occurs. For these weaker storms, the signature isn't quite as clear. So I just bring that up here, and you can see there is a peak here during the weaker storms, and this storm has a peak over here. Okay, so this does seem to be related to the storms, although for these weaker storms, it's not a very clear signature. But what's really interesting about this quantity is if you go after the peak here, which isn't particularly dramatic, you find that the maximum TC globally has its lowest value right after this peak. Well, that's the recovery phase. So these are pretty intense storms, and they have pretty intense recovery phases. The recovery phases of storms are characterized by big depletions in TC. So this simple index of global maximum TC reaches a peak during the storm period and then reaches a minimum after the storm period. And I show that minimum here, and I show that minimum here. So all the storms, except maybe the green one, showed that. This is, okay. So to summarize, we want to make a tractable thermosphere-ionosphere forecast, and what we forecast is critical. After analyzing what we call a forecast bust for the high-speed stream storm, we found that we had problems with the proxy F10.7 driver, and also pre-storm and high variability of the thermosphere-ionosphere makes it difficult to predict exactly the conditions. These unseen drivers, these highly volatile conditions in the thermosphere are difficult to forecast. But a global maximum TC may be something we can reliably forecast, particularly for the larger storms. It's driven by the physics of prompt penetration electric fields. I didn't have time to go into that physics, but it's a physics that, even though it's somewhat understood, the physics-based models could be improved significantly to predict it. And so combined with probabilistic BZ and predicting something like global maximum TC, particularly for the more intense storms, we think that's a tractable forecast. So thanks very much. That's mine.
Okay, maybe one question? Okay, I've got one question, actually. This proposed index, typically, I like to think of indices as having this particular application in mind. What specific uses do you envision for it?
Right, so this would actually be useful for applications because when you have large increases in TEC, those are correlated with large GPS errors. And also, when you have these large penetration electric fields, the TC increases tend to occur at a wide range of latitudes, and you get large TC gradients, particularly at mid-latitude. So there is a direct benefit to applications.
All right, thank you. So let's see. Our next talk is from John Emmert, who will be talking about thermospheric mass density model error variance as a function of timescale.
All right, thank you, and good morning. So I'll be talking about results from a study characterizing the spectral characteristics of thermospheric mass density model errors. That is the dependence on data minus model residuals variance on timescale as well as on solar cycle and altitude. So this is a talk about uncertainty, and to be of practical use, any prediction should be accompanied by an uncertainty. But the uncertainty must itself be estimated, and in many cases, that's actually much harder than making the actual prediction. And this is because measures of uncertainty, such as variance, are statistically quite volatile, so that a large sample size is needed to reduce what I like to call the uncertainty of the uncertainty. So in this talk, we'll be looking at the uncertainty of thermospheric mass density, which is a critical parameter for low Earth orbit prediction. And that's an application that requires very accurate estimates of uncertainty, for instance, for collision avoidance purposes. So for example, this graph here shows how simulated density forecast errors affect the orbit prediction errors. So for a 10 centimeter object in a 400 kilometer circular orbit, the possible spread of along track positions increases with increasing forecast time to about 500 kilometers. This is a huge source of error in orbit predictions. In the astrodynamics community, this need to get a handle on what this uncertainty is known as covariance realism. Also, following up on what Tony just talked about, there's a strong connection, at least on global average scales, between thermos mass density and the ionospheric electron content that Tony presented in the last talk. So now, the most commonly used metric to characterize model uncertainty is the root mean square of data minus model residuals, or a sample of those residuals. But this scalar metric obscures the spectral content of the errors. And for the orbit prediction errors depend on the time history of the density areas via a double integral with respect to time. So it's critical for this application to characterize the spectral content and the density error spectral stochastic process, and not just the uncertainty at a fixed time. So to do this, we analyzed a 40-year time series of global average density derived from two-line orbital elements, as well as a 10-year time series of local densities derived from the CHAMP accelerometer. And in addition to the high cadence CHAMP accelerometer data, we also examined daily averages of that data in order to better connect to the longer time scales represented by the orbit drive densities. Now, the actual parameter that we analyzed is the difference in log space between the density measurements and the NOAA-Space empirical atmosphere model. So this is essentially looking at the relative differences between the data and the model, and that's our analysis parameter. So here I'm showing a plot of the power spectral density as a function of log frequency, but for ease of interpretation on the x-axis I'm showing the corresponding period starting from 2 minutes on the right-hand side all the way up to 40 years on the left-hand side. And for the TLE data, I also processed the subset of data that overlaps with the CHAMP accelerometer data. And you can see that there's good agreement in those two spectra, which reflects the underlying good agreement between the actual densities of those two data sets. Now, for each of these power spectra, you see that there's a general roughly linear decrease in power in log power with increasing log frequency, and this suggests a power law stochastic process for these density errors. However, there is an enhancement here near 27 days, which we think is probably associated with the solar rotation period. Another thing I want to point out is you'll notice the TLE spectra drop off sharply at timescales shorter than 5 days, and this reflects the temporal resolution of those data sets. With orbit drive densities, your trade-off is there, 3 to 5 day temporal resolution. Now, looking at the higher resolution CHAMP data at shorter timescales, at suborbital timescales less than an hour and a half, we find that there's a comb-like structure in the spectrum, and we don't fully understand this yet. We think it might be a reflection of possible latitude-dependent biases between CHAMP and NRL-EMSIS. But these timescales are much more difficult to interpret because they're convoluted, that the temporal variance of these timescales is convoluted with the spatial variance as the satellite goes around the orbit. So we're going to focus mainly on timescales longer than 2 hours here. Now, power spectral density is a somewhat awkward parameter for characterizing error variance because it's typically quite noisy. These are actually smooth power spectral densities, not the raw dense power. And the scaling, as you can see here, also depends on the frequency bins, which typically, if you do an FFT, depend on the length of the time series. So instead, we consider the cumulative power, which is basically the sum of the power starting at the lower frequency up to higher frequencies. And that's shown here in these plots. So this choice facilitates combining spectra from different instruments. It also provides a smoother basis for characterizing the error variance as a function of timescale. So one feature of this is that if you look at the cumulative power at the highest frequency, that it's actually equal to the overall variance of the data set. Also on the right-hand side and subsequent plots here, I'm showing the root variance expressed as a percentage density error, so this is a parameter people are more familiar with. when looking at density errors. So we can, in order to get a, let me go back a little bit so you can see that again. So in order to get a continuous representation of the error variance across all these timescales, we can add the higher frequency CHAMP variance to the lower frequency orbit-derived variance to get this continuous cumulative variance. And as you can see, at 2 hours, we reach a variance that corresponds to about 20% density errors, and at the very shortest time scales, we find about 25% estimate. And we can also adjust the CHAMP daily averages to downward so that we can see that its frequency dependence agrees very well with the TLE-derived densities. Okay, so with the TLE data, we also have different altitudes that we can look at. So at 3 different altitudes here, we find that the variance increases with increasing altitudes, which can be understood as the contribution of a temperature error in the empirical model to the density errors. So we constructed an empirical model of these cumulative variances with a slightly quadratic dependence on log frequency as well as a linear dependence on altitude. And this empirical model ignores the enhancement at the jump in cumulative variance at 27 days that we saw in the power spectral density earlier. However, other than that, it seems to do a reasonable job of representing the increase in cumulative variance with increasing frequency. We also took a look at the solar cycle activity dependence of the variance. And we did this by splitting the TLE-derived densities into 2-year segments and computing the cumulative variance function for each 2-year segment, and then splicing that onto the overall variance timescales longer than that. And so you see the results here, which are color-coded by F107. At first glance, you would say, well, this isn't very well organized by F107 at all, but on closer look, we found that on timescales less than 25 days, the variance has a maxima at the solar minima, and on timescales greater than that, the variance tends to peak in the descending phases of the solar cycles. And we constructed an empirical model of this effect using the 2-year average F107 as an input argument with time lags of 0 and 2 years, and that's shown here with a dotted line, which seems to do a decent job of representing this time-scale dependent feature of the solar activity effect. Okay, turning to shorter timescales, we used the CHAMP data divided into 27-day segments to examine the cumulative variance from 5 days down to 2 hours, and that's shown here. The red here is the overall average, which is the same one I showed in the earlier plot. Now, looking at the solar cycle and altitude dependence using this data set is more difficult because the sampling of the parameter space is much sparser. This is basically showing the altitude in F107 sampling of the CHAMP data. However, if we assume a linear dependence on each of those variables, we find that the variance, again, increases with increasing altitude and also increases with decreasing solar activity. And this is similar to the TLE results we found on timescales less than 25 days. So we can put these two empirical models together to get a combined cumulative variance from 40 years all the way down to 2 hours. And this is just showing an example of that here for solar minimum. So we estimate then that the cumulative variance all the way down to 2 hours at 250 kilometers is about 12%. At 400 kilometers, it grows to 22%, and at 550, it's about 27%. So one application of this is that we can use this approach to diagnose the relative performance of different thermosphere models. And so, for example, here I'm comparing the cumulative variance of the TLE residuals with respect to the NRL-IMSIS model as before, and with respect to the global average mass density model, which is an empirical model actually developed from the TLE densities. So you can see that GAMDM residuals are less than the MSIS residuals, and this is not surprising because the GAMDM model was trained using the TLE data. However, most of this difference actually develops on timescales longer than 5 years. On the shorter timescales, the difference in the cumulative variance is roughly constant, which suggests that the models are performing similarly on those timescales. So this is very useful diagnostic, and it could be applied to other models as well as these two. This is just an example. So in summary, we find that the power spectra of thermospheric mass density model errors approximately follows a power law process down to periods longer than one orbit, except that there's an enhancement near about 27 days. And if we look at the cumulative variance, and we find that it depends on the time scale. So this is not a white noise process. There's a more complicated stochastic process going on here. The variance increases with altitude, at least up to 600 kilometers, and then it also depends in a fairly complicated way on solar cycle on timescales less than 5 years. So using these results, we constructed an empirical model that combines both the TLE drive densities and the CHAMP accelerometer data. We still have more work we'd like to do on it. We need to add other accelerometer data, namely that from the GOCHI, which is a little bit lower altitude than CHAMP, as well as GRACE, which is a little bit higher altitude to help give more, fill in some of those gaps. We'd also like to tackle the suborbital problem, which seems very interesting. It's more complicated, as I said, because the temporal and spatial variants get convoluted together. However, there does seem to be a lot of power in that part of the spectrum, which would be very important to see how that would then project onto orbit prediction areas, because it would accumulate, that power will accumulate in the orbit prediction areas. And then finally, it would be interesting to see how different solar industries perform as density proxies, thermospheric mass density proxies, as a function of time scale, which hasn't been done a whole lot before. So I'll leave it there, and thank you very much for your attention.
So we have time for one question. Bill?
You nicely stuck to the conclusions that you were allowed to make based on the data there. But I'm wondering, globally averaged densities or variances kind of sweep under the rug, things that may be happening low down suborbital time scales. And do you have speculation, conjecture, whatever, about what might be most strongly influencing that variance?
We haven't looked at it yet in much detail. We know that there are latitude-dependent biases between the empirical models and these accelerometer data, and it's not clear yet whether it's the model or the new data that are inaccurate. But that is one thing that could cause those spikes in the power spectral density. Yes, it is the smaller timescales are very important. We definitely want to look at them from a error estimation point of view. As I said, there's a lot of power there that could accumulate in the prediction errors. So, in terms of the actual prediction itself, it doesn't have much effect. And the global average density is important for a reason for orbit prediction, because the mean of the prediction tends to be zero. It's just the variance is what we're talking about here, but the mean tends to be zero, and all these fluctuations tend to average out in the prediction, but not in the variance. And so that's why I think it's important to look at those smaller timescales. Did that answer your question, more or less? Sorry.
All right. Thank you very much. So Antti Pulkkinen couldn't quite make it here. So on his behalf, Bob Weigel will be presenting development of new geomagnetic storm ground response scaling factors for utilization and hazard assessments.
Yes, thank you. So, yeah, Antti is going to arrive tonight, so he asked me to fill in at the last minute here, and I shall try. And so the discussion is on the development of a new and revised geomagnetic storm ground response scaling factors to be used for hazard assessment in geomagnetically induced currents. And in terms of the background, the FERC, Federal Energy Regulatory Commission, a new standard now requires the power industry to assess a hazard posed by a so-called 1 in 100-year extreme geomagnetic storm event. That order came out several years ago, and in order to actually answer the question of what the likelihood is and what the magnitude of the event would be applicable at different North American electric power stations, a working group was put together that involved a collaboration between scientists and electric power engineers. And one of the outcomes was an actionable benchmark that takes into account the core physical properties of extreme storms. And this report was published in 2013. And so what we're doing now is actually using some of the new data and some of the new ideas and models to revise these benchmarks. And I'll give a discussion of that shortly. So just as an example of the type of analysis we do, the vertical axis on both of these is the number of 10-second values of an electric field that was measured per 100 years. And to generate that histogram, took a image magnetometer chain data, ground magnetometer chain data, which is north-south magnetometer chain in Finland, and they have available 10 seconds high-resolution data, and we applied the ground conductivity model from two locations in Canada, one in British Columbia and another in Quebec, and the ground conductivity model takes an input of the ground magnetic field and produces a prediction of the electric field. And one of the limitations of those types of models is that they're one-dimensional, and so they'll predict the same electric field in the north and north-south and east-west direction, and they tend to be, these 1D models tend to be based mostly on considerations of local geology, and so they're very much an estimate. And so towards a better way of looking at this is to develop a 1 in 100-year benchmark event. We took the ground magnetic field waveform from the March 1989 Ottawa Geophysical Observatory recordings, and so and then we modeled the peak geoelectric field that you would measure based on two factors. One is it's a scaling factor, so it's relative to what would be observed in Ottawa given that conductivity structure, and so that's that prefactor there is that reference point. And then there's a alpha factor, which is the geomagnetic latitude scaling. So of course, as you go to lower latitudes, lower geophysical latitudes, the fluctuations that you're going to observe are smaller. And then more relevant for today is a local ground conductivity, a so-called beta factor, that is referenced and is measured with respect to the Quebec 1D ground response. And we use the Quebec 1D ground response since it's one of the worst ground conductivity structures in terms of producing large GIC events. So it's a worst case scenario type of model. And so from these, actually, yeah. Okay, and then the 1D beta factors are developed by using initially were developed by using these, a ground conductivity model from based on Fernberg 2012. And again, it's a 1D model, and it essentially breaks breaks the United States into about 20 different physiographic regions. And from those, we can derive a scaling factor that tells us how large the geoelectric field can be predicted, will be predicted to be based on your geomagnetic location. And an example of how these were developed is shown here. The left panel is for a March 1989 event, and the right panel is for October 2003 events. And so what was done is it took about 60 ground magnetometer data sets from the Intermagnet database, and we essentially measure the distribution of the maximum values of the geomagnetic field H, the horizontal component, max dBdt, and also the maximum geoelectric field. And so you can see there's a clear scaling factor that needs to be accounted for based on geomagnetic latitude. And now onto the new work is, it's based on a really great new data set from the EarthScope project. And essentially, EarthScope, you can see on those, each one of those dots there represents a site where they made simultaneous measurements of the ground magnetic field and the electric field for about 2 weeks. And these are transportable arrays, so they just move them across the surface. And this has been going on for about 10 years. And now they have a very, very good coverage of the United States from which we can derive ground connectivity models. And so essentially what is done with that data is to develop a conductivity model is you take the locally measured electric fields and magnetic fields and you compute this frequency-dependent impedance function, which tells you, given a magnetic field, what the electric field will be. And these, we don't use them for this purpose, but the primary motivation for developing these impedance tensors was to understand something about the structure of Earth's layers. But here we're just using it as a transfer function and just using it for prediction. And this is a sample of about a 2-week set of measurements that were made at a Midwestern site. And so this is the results. So essentially we take, each one of those sites has its own impedance tensor, which represents the ground conductivity. And we pass those benchmark geomagnetic storm event scenarios, ground magnetometer measurements, through these. And from that transfer function, we're able to compute the geoelectric field. And you can see pretty clearly here is that both the raw and the smooth scaling factors are significantly different from one and have a pretty fine-grained dependence on spatial location. And so, and it may be difficult to see, but that's a log scale on there for beta. So 0 is a factor of beta of 1, and we have variations on the order of 10 to 0.1 based on that initial version of those scaling factors that came out. Okay, and just to conclude, we utilize the full EarthScope magnetotelluric surface impedance to characterize the ground response based on this NERC benchmark event framework. And we've computed these revised beta scaling factors that can be directly applied to compute the geoelectric field at any point of interest. And and this work is forthcoming in a paper in 2018. So, thank you.
Okay, time for one question. I'm gonna keep scanning the whole room here. Okay, well, thank you very much. Yeah. Okay, let's see. Our last speaker will be, I think it's Greg Lucas, calculating realistic voltages across the U.S. power grid utilizing measured impedances and magnetic fields.
All right, everyone, so thank you. Okay, so I'm Greg Lucas, and I'm a current postdoctoral fellow under the Mendenhall program at the USGS in the geomagnetism program. And so what I'll be talking about is calculating the realistic voltages across the US power grid. And so what we're actually talking about here is how the space weather variations in the magnetic field are actually coming down here and affecting us on Earth. So we get these really nice magnetic fields, right, that are changing in time, so we get a magnetic field time series. And then we also have the solid Earth that's very complex. And so the solid Earth is acting like a filter for us, and it actually filters these magnetic fields, which induces then geoelectric fields within the Earth itself. So these geoelectric fields that we're talking about are going on in the surface of the Earth. And so then these geoelectric fields can induce quasi-DC currents within transmission lines. And so these electric fields that we're talking about are not large. They're volts per kilometer under intense storm conditions. So they're very small, but these transmission lines are generally grounded over very long distances. So when you start to do this integral, you can get significant DC voltages that arise in AC power lines, affecting their transmission characteristics. So what's traditionally been done here, as Bob was talking about in the previous one, is using physiographic regions. So the USGS has this complex map on the right of all this different geology going on within the surface of the Earth. And then these got reduced down into different physiographic regions. And these are 1D regions with different conductivity. So estimates based on broad assumptions of what the rock characteristics are at different depths. And so you get these different 1D profiles depending on which region you're in. And so that impedance tensor then looks like the bottom right there. So we get this one-dimensional skew-symmetric impedance tensor with these assumptions. So now, though, we have all these magnetotelluric measurements that have gone out. So over the last 10 years, the NSF Earth Scope, led by Oregon State University and a few sites run by USGS as well, have gone out there and actually co-located electric field sensors with magnetometers to actually get an empirical estimate of this impedance tensor. So now we have this fully filled tensor up there describing what's going on within the Earth underneath our feet. So we know what the sort of Earth filter is at all of those dots now across there. And the big takeaway here is that no matter how many 1D regions you try to break this up into, so you can keep going to more and more coarse 1D regions, but your magnetic field is always going to be perpendicular to the electric field with that 1D assumption. So this now allows us to actually start to turn the geoelectric vectors around. So we get a little bit of directionality with these geoelectric fields. So what we need for this then is the magnetic field input. So the USGS and NRCan here in North America measure the geomagnetic variations. And so this is just giving a quick snapshot of the March 1989 storm. So I'm going to be talking about the March 1989 time series here, so 2 days during that event. And the image on the left is the magnetic field time series, so the horizontal, the north and south component of the magnetic field at the USGS Newport station. And then the right image is the magnetic field at Fredericksburg. And we can see these large spatial and temporal variations in these measured magnetic fields just based on where you are. And so we can also see that they're very sparsely spaced. So we don't have a lot of observations, in the Midwest or anything either. So we need some kind of estimate to get there. And so if we do a physics-based interpolation, so we use spherical elementary current systems here. So we derive a current system that we can then project the magnetic field onto all of these impedance tensor sites. So this is what the magnetic field would have looked like during that March 1989 storm at all of these sites. And so you can kind of see the broad structure going throughout there, throughout the US. And then what that enables us to do is produce a magnetic field time series at every single one of these magnetotelluric stations. So just to note, on all the plots I'll be showing here too, it's all logarithmically scaled as well. So some of the variations you see are actually quite large in there as well. Okay, so we have that magnetic field time series at all of those sites. So now we can run that through the empirically derived filters that we have for the Earth response as well to get the geoelectric time series. And so on the left, we have what that looks like with the 1D physiographic regions. So again, these are all geoelectric fields that are going to be perpendicular to what our magnetic field input is. And we can see that there's large structures, again, going on there, following the magnetic field variation in general. And there's not a lot of amplitude variation as well. Whereas if we look at the image on the right with the impedance tensors, we can see that there's actually significant variations, not just in the amplitude, so there is amplitude variations as well, but there's also a lot of directionality dependence in there as well. So the vectors are kind of going all over the place there. So there's large amplitude variations in the Appalachians, as we saw in the previous talk as well. But these vectors kind of go all over the place. And so we need to take this into account when we're actually calculating the voltages within the power grids. So just a quick snapshot of what's actually going on there is if we look at the 1D assumption, they're all pointing in the same direction, all vertical, and we have a few different physiographic regions in this area, but the amplitudes are all pretty similar. But then if I go and look at actually what each of these MT sites in this region is, the vectors are going all over the place, the amplitudes are all over the place, so there's some that are producing almost no geoelectric field, and then there's others that are several volts per kilometer in there as well. So we really need to get this fine scale structure understood in this. And so now if we go and look at where all these transmission lines are across the United States, so we have all the transmission line information here, and we can actually integrate what that geoelectric field was throughout the course of time. And so in the 1D assumption, we get the broad kind of increases and decreases again. And there's also a few other structures that appear, but it's kind of hard to tell, what's the difference in a plot like this. So if we just take a quick snapshot of it, we can see that there's just all kinds of new features that arise in these voltages that are calculated across transmission lines. So there's significant differences of over 100 volts in many transmission lines, both higher and lower. So there's some that are producing less voltages than with the 1D case, and some that are producing much larger voltages as well. So we get these large discrepancies there. So I've been showing the March 1989 geomagnetic storm, and so that is well reported. So all the utilities have gone and actually reported some of their anomalies to the NERC reports, and so I've gone in there and looked at those and looked at actually when different issues were reported in different regions of the US. And so that storm is significant because there was many blackouts in Quebec, and so everybody knows about this, right? This is the large storm within the most recent history here, but there was also numerous storms reported in the US too, or numerous issues in the utilities reported in the US. They didn't cause blackouts, but they were still reported by the utilities. And so if we look at just a couple of snapshots in time and what these new magnetotelluric impedance tensors will actually show us there, we can actually see large voltages in the northwest during this time and relatively quiet time around the east coast at this snapshot. And so that's actually, it correlates well with what we are seeing in the reported issues. And then if we go to a little bit later, so about 3 hours later during this storm when DST was maximum there, we can see that it totally shifts directions. So now there's all kinds of voltages in the east coast being reported or being calculated in the transmission grid, whereas the northwest is now pretty quiet. And so that correlates well with all the issues that were actually reported by the power company. So we can sort of start to get an idea of these different time scales on when these magnetic fields are actually moving over the Earth and inducing the voltages within the transmission lines. All right, so kind of in conclusion is that to get an understanding of what is realistically going on within the power lines, we actually need these empirically derived measurements. So these new empirical measurements that have been undertaken by the NSF EarthScope program help us immensely in understanding kind of how the solid Earth filter is influencing these geoelectric fields that we're calculating. And we were using the USGS and NRCan magnetic field measurements to then understand so we've got the magnetic field measurements, we've got the magnetotelluric measurements, and now we can get these voltages across transmission lines. And notice that I haven't gone to the geomagnetically induced currents because a lot of that is that information isn't really known, what the grounding resistances are and what the network topology is. So the idea here is that these guys can take this information, calculating these voltages here, and apply that with their engineering knowledge of their system. So the individual utilities can use this to then calculate what are these geomagnetically induced currents, and where maybe will I have some issues going on within my grid itself. And so with that, I'll just leave the kind of three images here, so the three videos showing how we are going from the magnetic field calculated at all of these magnetotelluric sites to then getting the electric field, which we then integrate into the calculated voltages across all of the transmission lines. So thank you.
Questions? Yes.
So the electric field varying so rapidly spatially, how did you know how to do the interpolation to do the E.dl calculation?
So those are all just calculated at each time step. So every time step I have some geoelectric field there, and I do the integration, and that's what I get for my voltages there.
But you don't have the E field where the transmission lines are, right? So
The interpolation between points is what you're saying.
how do you interpolate that very stochastic looking field map with the 3D?
So right now we're assuming that we have an electric field at one spot and then just a linear interpolation between the two. So there's about a 70-kilometer difference between these NSF Earthscope sites. And so within there, we don't have any extra information about this. And so if there's a higher density of measurements in some location that we can utilize, then we can get the higher spatial structure features. But right now, yeah, we're just interpolating that between there.
Okay, any other questions? Okay, yes.
So you showed results for where you saw correlation with between power grid anomalies and the voltages you predicted.
Yeah.
You were just showing that for the cases of 3D impedances, correct?
Yes, so this is the realistic
Do you see any
sort of
correlation
impedances.
when you just use the 1D impedances?
So there is sort of broad structure in there when I'm using the 1D impedances, because sort of one of the largest drivers is the magnetic field itself, right? And so, yeah, we get that, but we don't get these finer kind of spatial structures, I guess, appearing in the 1D calculations then. But there is still a broad correlation, yes.
All right, no more questions. Let's thank all our speakers one more time. And I'd like to remind you guys there's more discussion, more presentations tomorrow morning in the same room, 8 to noon or 12:20. Poster session tomorrow afternoon, and our final poster session Wednesday morning. So hope to see you all. There's a lot of good material across all the sessions. Thank you.